Hello, our paper is Voronoi Spaghetti and VoroNoodles, topologically interlocked, space-filling, corrugated, and congruent tiles. This is a joint work by Cassie Mullins, Matt Ebert, Dr. Ergun Ackelman, and Dr. Vinayak Krishnamurthy. Our presentation is organized in 6 sections: summary, introduction, previous work, methodology, implementation, and conclusion and future work. We'll first start with the summary. In this work, we introduce an approach to model topologically interlocked corrugated bricks that can be assembled in a watertight manner, space filling, to design a variety of spatial structures. Our approach takes inspiration from recently developed methods that utilize Voronoi tessellation of the spatial domains by using symmetrically arranged Voronoi sites. However, in contrast to these existing methods, we focus our attention on Voronoi sites modeled using helical trajectories, which can provide corrugation and better interlocking. For symmetries, we only use affine transformations based on Bravais lattices to avoid self-intersections. This methodology naturally results in structures that are both space-filling, owing to the Voronoi tessellation, as well as interlocking by corrugation, owing to the helical trajectories. The resulting shapes of the bricks appear to be similar to a variety of pasta noodles, thereby inspiring the names Voronoi Spaghetti and VoroNoodles. Our next section is the introduction. In this work, we demonstrate that it is possible to guarantee topological interlocking through corrugation. Our approach is based on decomposing a given volume using helical ruled surfaces as Voronoi sites that populate volume using Bravais lattices. The shapes are still obtained by layer Voronoi decomposition, which is also critical to obtain strong corrugation. Layer by layer Voronoi decomposition also guarantees to obtain genus 0 surfaces, and the resulting tiles can always be assembled. An important property of this approach is that it provides access to a large design space to produce topologically interlocked tessellations. Using this approach, we introduce 2 unique varieties, namely Voronoi Spaghetti, shapes that have the same cross-section akin to a swept volume. This flexibility in design space is quite helpful to systematically search for new tessellation forms. Our general idea is based on using screw shapes as Voronoi cells. To picture mentally how we get corrugated brick regions, imagine that n number of screws screwed into a thick architectural shell or slab. We partition this cell into n number of brick regions, where region I consists of all points closest to screw number I. This operation naturally creates desired corrugation boundaries between the brick regions. It should be clear that shapes and placement of screws play an important role to obtain interesting corrugated bricks. The first requirement is that no 2 screws intersect with one another. This is not physically possible, but our virtual screws can potentially intersect with each other if we randomly place them. To obtain a nice decomposition of the space, we also need screws to be placed as uniformly as possible inside of the shell. This means that no 2 screws can be close to one another, and there should not be any large region left without a screw. The representation of screws can be obtained by curves and ruled surfaces that are defined in a parametric domain. They are defined by trigonometric functions to control frequency of corrugation intuitively. The intersection of screw shapes with any z-consistent plane layer is guaranteed to be a point or a line. With points and lines, it is easy to obtain uniformly discrete or relatively dense distribution in each layer. This further allows one to pack long curves or ruled surfaces as close as possible to each other without intersection. Our next section is previous work. Topological interlocking is an important concept developed for material science applications. Topologically interlocked assemblies typically consist of a single congruent tile that can be arranged in such a repeated way that the assembled structure is composed of rotated and translated versions of the single tile and can be held together by boundary constraints. If the bounding tiles are fixed, equivalently if there is a peripheral force applied to the bounding tiles, the internal tiles are kinematically constrained to hold their positions in space, simply owing to the geometric interfaces between the mutually neighboring tiles. In other words, in these assemblies, Each tile is kept in place by local kinematic constraints imposed through its shape and mutual arrangement of all the tiles. Even though there exist works that utilize similar approaches to obtain topologically interlocked tiles, such as Delauney Lofts and generalized Abel tiles, they do not provide corrugated boundaries. Providing topological interlocking by helical ruled surfaces as Voronoi sites leads to intuitive and generalizable design mechanisms to obtain desirable corrugated boundaries. For instance, an intuitive way of defining such a ruled surface is rotating and scaling a line while translating its center. To demonstrate this intuitive approach, we chose a concrete class of helical trajectories, wherein we mapped the motion of each Voronoi site based on the transformation matrices induced by the helix. Our results show that the resulting congruent shapes coming from the helical trajectories demonstrate strong potential for topological interlocking assemblies by providing corrugated boundaries. Our next section is methodology. Voronoi spaghetti is obtained by using a point which is translated in the z direction along a spiral curve. Then, these curves are translated by two 2D vectors to populate the space. This operation can also be viewed as translation of a rectangular or hexagonal grid and using the motion of the grid vertices as Voronoi sites. This example shows a Voronoi spaghetti as an extruded 2D honeycomb. Since the two honeycomb is exactly the same in each layer, each congruent tile is the same in each layer. Since this is obtained by a single curve, the resulting congruent tiles in each layer are convex polygons. In this particular case, they are all regular hexagons. In this case, the resulting shape is long and skinny, which owes to the name Voronoi spaghetti. Our most important contribution to obtain corrugation is to use layer-wise Voronoi instead of 3D Voronoi. In layer-wise Voronoi, we only compute Voronoi in a thin layer, ignoring the rest of the space. This operation gives us prisms in each layer. These prisms together form the desired Voronoi spaghetti. This example shows why we need layer-wise Voronoi. The result of 3D Voronoi may not even be assembled. 3D Voronoi also does not provide nice corrugation. This example compares both methods. An additional advantage of layer-wise computation is that it creates aliasing by creating the staircasing effect, which can improve interlocking. Here are some examples of VoroNoodles with different 2D honeycombs in each layer. This is obtained by using a ruled surface as a Voronoi site, created by scaling a line. Each layer is translated using a curve. To obtain the ruled surface, we scaled and rotated a 2D vector along this curve. For VoroNoodles, we replace points with lines. We also rotate and scale lines. In VoroNoodles, we also use layer-wise Voronoi. In each layer, we again compute the Voronoi decomposition independent of other layers. In this case, the shapes in each layer become different. Since each layer is different, we obtain better corrugation. These two examples visually show that Voronoi sites of VoroNoodles are ruled surfaces that are obtained by rotating and scaling lines. The most important concept in this case, we guarantee that the lines do not intersect with each other. The line in each layer will stay inside the parallelogram, defined by its Bravais vectors, v0 and v1. Our next section is implementation. Here are two examples which were created using Houdini. This example shows us that each layer we use curves. Our next section is conclusion and future work. This method can also be used to cover surfaces. For general surfaces, there is a need to use geodesic distance and to decompose offset surfaces independent from each other. More complex structures can be obtained by using a variety of curve networks, trees, and graphs. Staying inside of Bravais lattice is straightforward by using the convex hull property of B-splines and Bezier curves that is directly resulted from their barycenter formulation. Thank you all for listening to our paper.